Okay, section 19.9 finally takes a good look at electrolytic cells and the process of electrolysis. So figure 1916 below shows kind of the basic foundational principle of an electrolytic cell, where instead of using a spontaneous chemical reaction to provide electrical power, say to light a lamp, like we see over here at the voltaic cell, an electrolytic cell over here will use an external applied voltage source in order to drive a non-spontaneous reaction. And so in an electrolytic cell, the goal or purpose of the cell usually has to do with generating products in the electrolytic cell. Whereas in a voltaic cell, the goal or purpose of it is just to produce electrical energy. The products are a waste. And so they're really pretty different in their applications, even though they are both electrochemical cells. They're both subject to the Nernst equation and all of the redox chemistry principles that we've been talking about up until now. So using electrolytic cells, we can force the reduction of cations that are difficult to reduce chemically, like, say, sodium and potassium cations. Sodium and potassium metal are so reactive, they're so readily oxidized, that it's difficult to produce sodium metal or lithium metal from their cations. If you apply an external voltage, though, it becomes pretty trivial. You just need a high enough voltage source, and you can produce, or you can force the reduction of these ions. And that's how the alkali metals like sodium and potassium were originally discovered hundreds of years ago through electrolysis. Also, aluminum. Aluminum metal at one point was more expensive than gold, and like kings and queens would have aluminum cutlery and aluminum plates that they would use with their most distinguished guests because the aluminum was so precious. And that's because it was unknown at that time how to chemically reduce aluminum ores to produce aluminum metal. There's only a small amount of what's called native aluminum, or aluminum that is in its metal elemental form that occurs in nature. And so it was actually more rare and more precious and expensive than gold. Anyway, once electrolysis was discovered, it became trivial to reduce aluminum ores, which are minerals that contain aluminum cations, like, say, aluminum oxide or aluminum carbide or something like that, and to reduce those cations to form aluminum metal. So now aluminum cutlery, I dare say, would be considered a cheap alternative to something like stainless steel, let alone something like silverware that's actually made of silver. Okay, and it's notable that even though this is kind of easy to achieve, it still does take a lot of electricity. And if you're generating aluminum on an industrial scale, it takes a lot of electricity. So the country of Iceland is really interesting in that its economy is really focused on this electrolytic reduction of aluminum. Iceland has a lot of geological activity, volcanoes and things, and so geothermal energy is really easy for the Icelanders to generate. They extract energy from the hot spots, the magma and whatnot, to generate electricity. But it's also an island nation, and it's not possible for them to easily export that electricity. They're not going to string a wire from Iceland down to England or over to Sweden or Norway or anything like that. So what they do is they'll have barges from all around the world bring in their aluminum ore, and then they'll use the tremendous amount of cheap electricity that they can generate to convert that aluminum ore into aluminum metal, and then they'll send the aluminum metal out to be used. And this looks like an import of aluminum ore and an export of processed and purified aluminum metal. But the interesting backstory to this is that it's essentially a way for them to use their cheap electricity. It's a way for them to sort of effectively export electricity because that's their abundant natural resource. Okay, anyway, that's, I just think, an interesting application. So let me get rid of this actually. We'll look at another figure a little bit later. So in electrolysis, we're actually really interested in talking about electrolysis quantitatively. So we're going to do a little bit of math here. We can measure the flow of electrons using a new unit called the ampere. So 1 ampere, usually called 1 amp, is equal to 1 coulomb second. So remember, a coulomb is a measure of charge. And so if you move 1 coulomb's worth of charge over a time period of 1 second, then that is what an amp means. And remember, we can relate coulombs to individual electrons through Faraday's constant. Faraday's constant says that 1 mole of electrons is equal to 96,485 coulombs. And so we can ask a question like, find the mass of aluminum produced if an electrolytic cell runs at 0.575 amps. And that's about the current that maybe your average cell phone charger is going to output, not the fast chargers, but the old ones would run at about a half an amp. And you run it for 40 minutes. So what is the mass of aluminum that you could generate using this electrolytic cell? Now, we should recognize that we're going to be reducing aluminum 3+ to form aluminum metal. And so we require 3 electrons for every 1 mole of aluminum. Well, this is how you would set it up. Say 40 minutes. And then every 1 minute is 60 seconds. And then this 0.575 amps is going to give you a conversion factor between amps and coulomb seconds. We could kind of arrange this to say that 1 second is equal to 1 amp over 1 coulomb, right? And so here we've got seconds, and we'll say 1 second is 0.575 coulombs. 0.575 coulombs for each second is what 0.575 amps means. Okay, 96,485 coulombs is 1 mole of electrons. 3 moles of electrons is 1 mole of aluminum. And then finally, the molar mass of aluminum is 26.98 grams of aluminum for every 1 mole of aluminum. And this is going to give us a final answer of 0.129 grams of aluminum. So you can see how we're going to require a lot of energy if we want to produce tons and tons of aluminum like Iceland does. You could run your cell phone charger for about 40 minutes and only get a little over 1/10 of a gram. Oops. Okay, we could also look at something like a LiPo battery. Remember, a LiPo battery has lithium plus ions migrating from the anode to the cathode. And that migration is an electric current. Coulombs can apply to lithium ions just as well as to electrons. It's just one's positively charged and one's negatively charged. But because it's a 1 plus charge, it's really just a one-to-one comparison. So if you have a cell phone battery that has 3,000 milliamp hours, and that's kind of a typical cell phone battery charge, what that means is that it can operate over 1 hour of time at a current of 3,000 milliamps or 3 amps. And so we can ask the question, how many grams of lithium ions does this cell phone battery contain? It needs enough lithium ions to make this migration from anode to cathode in order to produce that amount of electrical current. So the way we'll do this is we'll say 3,000 milliamp hours. And the first thing, let's get rid of that hour, because an amp is a coulomb per second. The hour is not helpful, so 1 hour is 3,600 seconds. Okay, that's 60 minutes per hour and 60 seconds per minute, 3,600 seconds. And then we'll get rid of the milli. We'll say 1,000 milliamps is 1 amp. And then we'll say 1 amp second is 1 coulomb. So every amp second is going to produce 1 coulomb of current, or 1 coulomb of charge, I should say. Okay, and then 1 coulomb is, hold up, that's not right. 96,485 coulombs is 1 mole of lithium plus ions. Again, they're kind of a stand-in for electrons. It's the same thing. Electrical current, in this case, is the flow of lithium ions instead of electrons. And then 1 mole of lithium is going to be 6.941 grams of lithium. The fact that it's a 1 plus ion doesn't really matter. It's lost an electron. Well, electrons are tiny. They're only a tiny fraction of the total mass of lithium. So we can just use lithium's atomic weight off of the periodic table. And anyway, this is going to lead to 0.78 grams of lithium. So your cell phone battery has, just under 1 gram of lithium ions. And really it probably has a bit more than a gram, because realistically you can't migrate all of the ions from anode to cathode, so they probably overshoot it by a fair amount. Maybe you've got about 1 gram of lithium ions in your cell phone battery. So that's it for the calculations, but I do want to talk about a couple of different applications of electrochemistry. All right, so the first is electroplating. Sorry, one moment. Now, at the cathode of an electrolytic cell, reduction is going to occur. So you're going to have metal cations potentially reduced to form neutral elemental metal. Here we show how you can take any electrode, in this case they have an iron fork, and if you hook it up to a power supply where the other half of the cell is something like a silver plus electrode, then you can force the iron 2+ ions to plate themselves onto that iron object. For the reduction to occur, they need to accept an electron. They need to gain that electron, and the electrons are only available on the iron fork cathode. And so in order for that silver plus ion to be reduced to solid silver, it has to come in physical contact with the iron fork. And when it comes in physical contact with the iron fork and is reduced to solid silver, it will stick there. And so you can make a thin layer of silver over any electrically conductive object. In this case, it was an iron fork. It could have instead been something like an iron nail, and you use a zinc anode, and that's going to galvanize that nail by coating it with a thin layer of zinc. Or it could be a gold ring that you have a thin layer of rhodium over the top of it to make it look white. There are lots of other applications where electroplating is the way to make a thin, sort of uniform and pure layer of some metal on the surface of another object. So that is electroplating. Okay, one last application of electrolysis is electrolytic refining of metal ores. So suppose you have copper ore, but copper rarely in nature is going to be pure, and so what you have really is something that's mostly copper, and it's got small bits of magnesium, of aluminum, of iron, of gold and silver and platinum all mixed into it, because the way geology works, these metals do tend to come at least a little bit mixed together in the ores where they're mined. Well, what you'll do is create a cathode of a good pure sample of copper, and your anode is the adulterated copper that contains all these other metals. And you apply just the right potential that will cause the copper ions at the anode to be dissolved and form copper 2+ ions. And then those copper 2+ ions will migrate over to the cathode, and they'll be reduced, and so your cathode will grow and grow as more copper ions are reduced, while your anode disappears. Well, what about all the impurities? Well, for the impurities that are more easily oxidized, like magnesium or iron or aluminum, if you apply a voltage that is sufficiently high to oxidize the copper, it will oxidize them as well. But they don't get reduced at the cathode, because the cathode will preferentially reduce whatever has the highest reduction potential, which would be something like copper. Which would be copper. If you have just the right voltage, then copper will match that reduction potential exactly. And as long as there are copper ions in solution, they will be reduced and incorporated into the cathode instead of the iron or aluminum or magnesium. And so those other ions remain in solution, and you can just dump them out when you're done. What about the other metals that are harder to oxidize than the copper, like the silver and the gold and the platinum? Well, they're not going to dissolve at all. As your anode of adulterated copper is slowly dissolved through the electrolytic process, then those other metals will be left behind, still in their solid form. There's not any electric potential strong enough to oxidize them as long as you're carefully controlling that external voltage. And so they remain behind. They will, as that electrode dissolves away, they'll actually drop down to the bottom as a sort of a sludge. There's not very much there, but because these metals tend to be precious metals, it's very much worth it to then collect that sludge and put them through their own purification process to recover the gold and the platinum and the silver that were left behind. So this electrolytic refining of copper, it has two purposes. First, you get ultra pure copper out the other side that is going to be more valuable for use in sensitive applications. Maybe the copper pipe that carries the water through your house doesn't need to be pure copper, but if you're making electronics or something, then you're going to want a finer grade of copper. But also you're recovering all of those precious metals that were incorporated into the original copper sample. And so by recovering those, you can sell them separately as gold and copper and platinum and fetch a higher price for them. That makes this a very worthwhile process. So that is electrolytic refining of copper. And of course you could do this for any other metal. It's just a matter of adjusting the applied potential to perfectly match the metal that you're wanting to target. And that's it for chapter 19. I don't think I'm going to do any quizzes anymore. As you can see, I'm finding it difficult to keep up with the workload since I'm also tending my 3 children all day while my wife's at work. And so I think we work through practice problems here in these lectures. The quizzes are usually just a rehashing of those types of problems. And there are plenty of videos available on YouTube made by people with much more experience and better technical know-how than me. And so if you do want more practice than what we've done in our normal lecture videos, I encourage you to just search YouTube and you'll probably be able to easily find some. If you can't, then email me and I'll either point you to some videos myself or I'll make one for that special case. We will still continue to do lecture videos, and we'll have a midterm exam and a final exam as normal. But I just wanted to tell you there's not going to be any more quizzes. It's just too difficult for me to keep up with writing the quizzes and the keys and making the solution videos and everything else. So I'll make another video for you again tomorrow.